Screen is visible, students?
Yes, sir.
Okay. In the last class, I had started with the discussion on infinite line charge. I'll quickly brief up that. The infinite line charge is lying on the z-axis, right? And its line charge density is rho L coulomb per meter. It's a line charge density. Then its radius is r. We are considering the Gaussian surface as the right circular cylinder. Its radius is r. Then we have considered some portion on the right circular cylinder, that is ds, right? Ds is the area which we are considering to find the electric field intensity. Then the radial vector, the flux will be directed radially outwards on the surface of the cylinder, right? Flux will be on the surface of the cylinder radially directed outwards. Okay, this is the direction of the unit vector ar bar. Then the length of the cylinder is L. Okay, this is just an introduction to the, that is how the infinite line charge is placed and how we are considering the Gaussian surface and the area ds. So with this brief introduction, then we'll move on to here. The direction normal to ds is ar bar. As line charge is along z axis, there cannot be any component of d bar in the z direction. As the line charge is along the z axis, and hence if you are considering any charge on the z axis plus z axis, there will be equal and opposite charge on the minus z axis. Their effect or the z component of the electric field density, electric flux density, will be cancelled out due to the plus z axis component and minus z axis component, and hence we are not considering the z component of the electric flux density when deriving the equation for the infinite line charge. Okay. So d bar has only the radial component. It has only the radius component because it is the radius. It is directed radially outwards. It is directed radially outwards. It has only the radius component or the radial component. Okay. It is. It is on the surface of the cylinder. It is on the surface of the cylinder. The flux is lying on the surface of the cylinder at the radius r, and it has only the radial component or the radius component. So d bar has only radial component, therefore q is given by closed surface integral d bar dot ds bar. This is according to our Gauss law. The charge enclosed is given by the equation, the closed surface integral of the electric flux density with respect to the surface. This integration we have to consider for the surfaces. It is top surface of the cylinder, bottom surface of the cylinder, and the side surface of the cylinder. Okay, on this we have solved an example. If you remember at the beginning, on the right circular cylinder we had solved one example, right, to calculate the surface area of this cylinder and the volume of the cylinder by the method of integration, is it not? Integration is to be evaluated for side surface, top surface, and bottom surface. Therefore q is written as closed surface integral d bar dot ds bar for the side surface plus closed surface integral for the top surface of d bar dot ds bar plus closed surface integral of d bar dot ds bar for the bottom surface. D bar is dr ar bar. It has only the radial component. Therefore, I can write d bar as dr. Dr is the magnitude and ar bar is the unit vector along the direction of the radius. Ds bar is given by r d phi dz ar bar, which is normal to ar bar direction. Ds bar is r d phi dz ar bar, normal to ar bar direction. We have to consider the component normal to the ar bar direction. The component which is perpendicular to ds bar or that is normal to ar bar direction is r d phi dz ar bar. This we are borrowing from the cylindrical coordinate system. When we had begun with the classes initially, right, there we studied the cylindrical coordinate system, different coordinate systems, that is rectangular, cylindrical, and spherical. There we have come across this, that the area ds, which is perpendicular to the perpendicular to the surface ds along the ar bar direction, it is given by r d phi dz ar bar. R d phi dz ar bar. This is the equation that we are borrowing from the explanation of the cylindrical coordinate system. Okay. Therefore, d bar dot ds bar, that is d bar is dr r dr ar bar. Okay, then this ds bar is r d phi dz ar bar. Substitute, we get dr r d phi dz dr r d phi dz ar bar dot ar bar. It's a dot product, ar bar dot ar bar. Ar bar dot ar bar is how much? 1. It's a dot
1.
product of the unit vector with itself. Yes, it is 1. Correct. Therefore, this is equal to dr r d phi dz. Dr r d phi dz, because ar dot ar is equal to 1. Clear here? As the d bar has got only the radial component and no component along az bar and minus az bar, hence integration for the top surface and bottom surface, what they will become? It has only radial component. Therefore, integration for the top surface and integration of the bottom surface along plus z and minus z, what they will become? Integrations. Yes, please. The component of d bar is only along the radius. It is along only the radial direction because it is lying on the surface of the cylinder. Right? What about the electric flux density component along the plus z axis and minus z axis? That is for the top surface and the bottom surface. Yes. What it will be? Students, what it will be? Integration of the d bar dot ds bar over top surface and integration of d bar dot ds bar over the bottom surface. Yes, please. Anybody?
Sir, 0.
0, right? Because we know that the component of d bar along z axis and minus z axis is 0. Therefore, the integral will be of the top surface and bottom surface will be 0. There is no component itself. Therefore, it is 0. Okay. The only component that is existing is the side component for the side surface. Yes or no? Therefore, closed integral d bar dot ds bar for top surface is equal to closed surface integral d bar dot ds bar for the bottom surface, that is equal to 0. Hence, we have the q is equal to q equation we have written already. This is our q equation. So this q equation will be only for the side surface. Top and bottom integrals are 0. That is q will be equal to closed surface integral side surface d bar dot ds bar. Write it. This q is equal to closed surface integral d bar dot ds bar for the side surface. Substitute d bar dot ds bar whatever we have obtained. D bar dot ds bar is equal to dr r d phi dz. Dr r d phi dz. Substitute this. That is side closed surface integral dr r d phi dz. We know that we are integrating the side with respect to d phi and dz. Therefore, we have to take the double integral because we are integrating with respect to d phi, okay, and the dz. Dz varies from what to what? Dz varies from what to what, students? Dz. Can you tell me? Dz varies from 0 to L. 0 to L. This is 0. That is the reference, okay, or origin. Then this is varying up till L. L is the length of the cylinder. Therefore, the z axis is varying from 0 to L. 0 to L. What about the angle phi? Angle phi, it varies from 0 to 2 pi. It's a circular surface. Circular is 360 degrees. Correct? Therefore, phi varies from 0 to 2 pi and the length varies from 0 to L. Use these limits. Z varies from 0 to L and phi varies from 0 to 2 pi dr r d phi dz. That is further equal to r dr. This is r dr. Then integration of dz with respect to z is z over the limits 0 to L. Integration of d phi with respect to phi is phi over the limits 0 to 2 pi. Substitute these limits, we get z as L minus 0, that is L, then phi as 2 pi minus 0, it is 2 pi. Hence the answer will be q is equal to r dr L 2 pi. Okay, r dr L 2 pi. That is our answer for q. Then write the equation for dr. Rewrite it. Dr is equal to, I'm rearranging the terms. Dr is equal to q divided by 2 pi r l. Dr is q divided by 2 pi r l. This is our flux density in the radial direction. In the radial direction. That is d bar is equal to, if I consider the vector d bar, then it is magnitude along with the unit vector. Magnitude along with the unit vector, along with the direction. That is d bar is dr ar bar. D bar is dr ar bar. Dr we have calculated just now. It is q divided by 2 pi rl into ar bar But we know that the line charge density is the charge per unit length. Line charge density rho l is charge per unit length, q divided by l, that is rho l. Okay, therefore d bar will be equal to q by l is rho l. Substitute that in this equation. For q by l, d bar will be equal to q by l is rho l divided by 2 pi r ar bar coulomb per meter square. It is flux density, which is coulomb per meter square. Therefore, the equation is d bar is rho l by 2 pi r ar bar coulomb per meter square. Then find the equation for E bar. We know that D is equal to, what is the relation between D and E, students? Relation between D and E, equation between D and E, electric flux density and the electric field intensity. Relationship between these two is given by which equation? Anybody?
Sir, D is equal to epsilon times of the E.
Very good. D is equal to epsilon naught times of the E. Right. That is D is equal to epsilon naught E, or E is equal to D divided by epsilon naught. D is equal to epsilon naught E, or E is equal to D divided by epsilon naught. That is rho l divided by 2 pi epsilon naught r ar bar volt per meter. D is rho l divided by 2 pi r. Substitute that. That divided by epsilon naught means final equation will be rho l divided by 2 pi epsilon naught r ar bar volt per meter. Did we not get the same equation, students, when we derived using the Coulomb's law for the infinite line charge? That is rho l divided by 2 pi epsilon naught r ar bar or ay bar we got there. Yes or no? So we got the same equation there. 2 pi epsilon naught r ar bar volt per meter is the equation that we had obtained for the infinite line charge using the Coulomb's law also. The same equation was obtained. Therefore, it says that the results are same as obtained from the Coulomb's law. Okay, we have used the Gauss theorem and the Gaussian surface, and we have obtained the equation for the electric flux density and electric field intensity, which are same as that of we had obtained for the using the Coulomb's law. Okay. Any difficulty here, students, in this derivation? Any problem in this derivation, students? Any difficulty here for the infinite line charge?
No, sir.
Okay. Everybody understood? Any problem in understanding? Any difficulty? Any questions? If you are having any questions, we can ask. Okay, then we'll proceed. Next, students, infinite sheet of charge. The same as we did for the other two, that is for the infinite line of charge, we'll be similarly using the Gaussian surface and the Gauss equation, Gauss theorem, for finding the electric flux density and the electric field intensity for the infinite sheet of charge. Let us consider the infinite sheet of charge placed on the xy plane. This is the infinite sheet of charge, what you are seeing, the rectangular surface, the larger one, right? It is placed on the xy plane, that is in the plane z is equal to 0. If you are placing on the floor of your room, okay, the infinite sheet of charge, then its z component is 0, because you are placing on xy plane. Your floor is the xy plane where you are sitting in the room, right? Or if you are placing the infinite sheet of charge on that plane, then the z component will be 0. Z component will be, vertical component will be 0. Okay. Then we are considering this rectangular box as the Gaussian surface. This rectangular box as the Gaussian surface. This rectangular box cuts this sheet of charge. When we are placing this rectangular box, and we are considering a small area ds wherever this rectangular box is cutting the sheet of charge. Wherever this rectangular box is cutting the sheet of charge, infinite sheet of charge, that area we are considering it as ds. Okay, then d bar is the electric flux density which is perpendicular to the Gaussian surface. As I told you all to remember the points, that is, one point is the electric flux density is applicable only to symmetrical surfaces, or the electric flux density is perpendicular to the Gaussian surface. Gaussian surface is a surface over which we are applying the Gauss theorem or the Gauss law. Such surfaces are called Gaussian surfaces. Then for such surfaces, the electric flux density is always perpendicular. It is always perpendicular to the Gaussian surface. Okay. Therefore, here d bar is perpendicular to this Gaussian surface that we are considering, rectangular box. Then the direction, unit vector direction of the d bar vector, it is along an bar. If you are considering d bar in the negative z axis, then it is minus an bar. Am I right? If you are considering the direction of d bar from the top surface, which is in the arrow pointing away from the top surface, that is plus an bar. If I am considering the d bar from the bottom surface, then it is minus an bar. Then ds is the surface, Gaussian surface we have considered. Then rho s is the surface charge density. It is the charge per unit area. Charge per unit area, rho s. Rho l is charge per unit length, line charge density. Rho s is charge per unit area, that is surface charge density. Correct? It is the infinite sheet of charge with the charge density rho s coulomb per meter square on the xy plane with z equal to 0. Consider rectangular box as Gaussian surface which is cutting the sheet of charge to give ds is equal to dx into dy. Wherever this rectangular box cuts this infinite sheet of charge, there the area whatever is formed, it is length into breadth, because it's a rectangular box. For the rectangular box, what we are finding, what is the area that we are finding? The area is length into breadth, length into breadth. Okay, so it is dx into dy, dx into dy. Okay, this is dx, then this is dy, dx into dy. That gives the area of the this area, small area that we are considering wherever the rectangular box is cutting the infinite sheet of charge. Fine. D bar acts normal to the plane, that is an is equal to az bar, and minus an bar, that is minus az bar direction. An bar is equal to az bar and minus an bar is equal to minus az bar, because an and az, they are lying parallel to each other. They are lying same. Wherever is az, along the same direction the an bar is lying, and wherever is minus az bar, minus an bar is lying. Hence we consider an bar is equal to az bar, or minus an bar is equal to minus az bar. Here d bar is equal to 0 in x and y directions. Okay, if we consider d bar in x and y directions, because where the d bar is pointing, according to our definition of the Gauss law, or according to our assumptions of the Gauss law, what we are following the points, that is electric flux density is normal to the Gaussian surface. Electric flux density is normal to the Gaussian surface. That means at the side surfaces there is no component of d bar. There is no component of d bar existing at the side surfaces. The d bar component exists only perpendicular to the surface. Correct? Therefore, for the side surfaces, the d bar component is 0. That is, which are the side surfaces? X and y component. For the x and y component, the d bar components along x direction and y component y directions are 0, because d bar is always perpendicular to Gaussian surface. Hence, now d bar is lying along the z axis. The charge enclosed can be written as Q is equal to closed surface integral d bar dot ds bar. This is our Gauss law. That is, we are evaluating the integral for the side surface, top surface, and bottom surfaces. Evaluate the integral for top surface, that is integral d bar dot ds bar for top surface plus integral d bar dot ds bar for bottom surface plus integral d bar dot ds bar for side surfaces. Clear? But for the side surfaces, that is for along x and y direction, there is no component, and hence d bar dot ds bar is equal to 0, as d bar has no component in x and y directions. Now d bar is having only z component, that is dz az bar for top surface. Consider top surface separately and bottom surface separately. Top surface separately and bottom surface separately. Therefore, if I consider for the top surface, what will be d bar, students? It is dz into az bar. Yes or no? D bar is equal to dz into az bar. Dz is the magnitude, az bar is the direction, unit vector for the top surface, for this surface. D bar is, that is dz is the magnitude and az bar is the direction of the d bar for the top surface. Then what is the area ds bar? Area is length into breadth, that is dx dy. Then unit vector is the perpendicular unit vector, it is az bar. ds bar is dx into dy, length into breadth, and the perpendicular unit vector is az bar. Therefore, d bar dot ds bar. If I want to find d bar dot ds bar, because that is our LHS of the Gauss law, d bar dot ds bar is equal to dz az bar into dx dy az bar. This will be dz dx dy az bar dot az bar. Az bar dot az bar is unity, it is 1. Therefore, this will be simply dz dx dy, dz dx dy. Therefore, d bar, this is for top surface. Now write for the bottom surface of the rectangular box, bottom surface of the Gaussian box or the Gaussian surface. D bar is equal to dz is the magnitude, the unit vector. If you consider for bottom surface, for the bottom surface, the unit vector will be minus an bar or minus az bar, minus an bar or minus az bar. Clear here? That is what I am writing. D bar is equal to dz into minus az bar for the bottom surface. Its magnitude is same but opposite in polarity. Therefore, ds bar will be, ds bar is dx dy, that is same as that of the top surface, area is same, but the vector, unit vector direction is opposite, minus az bar, minus az bar. This is for bottom surface. Then find out d bar dot ds bar, that is dot product of d bar dot ds bar, that is dz dx dy, then minus az bar dot minus az bar, minus into minus is plus. Therefore, az bar dot az bar is again 1. Yes or no? Therefore, it will be simply d bar dot ds bar is equal to dz dx dy, dz dx dy. Then what will be the integral of top and bottom surface, students? Therefore, q, I can write it as closed surface integral dz dx dy, whatever we have got here, dz dx dy. Here, this equation, dz dx dy for top surface, plus for the bottom surface, dz dx dy. Then what is common? Dxy and dxy are dx dy are common in both the integrals. Okay, so if you take dz outside, then closed integral for top surface dx dy plus closed surface for bottom surface integral dx dy. If we integrate dx dy, this dx dy, if we integrate, what do we get? Dx dy is small component along x direction and y direction, right? If we are integrating these two, if we are integrating dx into dy, the area, then what we finally get? Dx dy is some small part, small portion of the area. Then if we are integrating this either for top surface or for the bottom surface, what do we get? Think. Adarsh, Shinde.
Sir, area total.
Exactly. Very nice.
Sir,
We'll get
total
the,
area.
yes, you are right. The total area of the rectangular box will be obtained, because dx into dy is small portion, it is a small area, right? Dx into dy. If we integrate that, we are getting the total area of the box. Okay, either it may be for top surface or for the bottom surface. Okay, if you integrate the top surface dx into dy, you are getting the total area. If you are integrating dx dy for the bottom surface, then also you are getting the total area. Okay, that is what is our next equation. So top surface closed surface integral dx dy, that is equal to bottom closed surface integral dx dy, that is the total area of the surface, that is a, that is area of the surface, total area will get. Okay, therefore I am taking this 2 equated to a, that is closed top surface integral dx dy is equal to bottom closed surface integral dx dy, that is equal to a. Then resubstitute in the previous equation. Here dz, you just take it outside, the top integral dx dy plus bottom integral dx dy, each are equal to a, so a plus a will be 2a. dz is common, closed top integral dx dy plus closed bottom integral dx dy, each one of these are a plus a will be 2a, a plus a will be 2a. Then the next equation will be q is equal to 2 dz a, q is equal to 2 dz a. Dz already we have taken it common. Okay, the integrals inside there will be a plus a, therefore we are getting 2a. Then the equation is q is equal to 2 dz a. Therefore q, what is the equation for q, students? The q is obtained by the equation from the surface charge density. Surface charge density is given by rho s is equal to q by a. Rho s is q by a, that is charge per unit area. Charge per unit area, that is our surface charge density. Yes, therefore q will be equal to rho s into a. Rho s is q by a, or q is equal to rho s into a. Substitute in the above equation, q is equal to rho s into a, that is equal to 2 dz a. So a and a will cancel, we'll get rho s is equal to 2 dz. If you are substituting this q is equal to rho s a in the above equation, excuse me, rho s into a will be equal to 2 dz a, or rho s will be equal to 2 times dz, 2 times dz. Therefore dz will be equal to rho s divided by 2. dz is rho s divided by 2. This is the z component of the electric flux density, what we are getting. Next we have to write it in vector form. The vector is d bar, that is the z component magnitude along with its direction, az bar. Therefore that I can write it as dz equation we have obtained here. Substitute that rho s by 2, rho s by 2 into az bar coulomb per meter square. Okay, rho s by 2 az bar coulomb per meter square. This is equation for d bar. Then what is the equation for e? E is equal to d by epsilon naught. E is equal to d by epsilon naught. Substitute the previous whatever we have got, rho s by 2 divided by epsilon naught. This will be equal to rho s by 2 epsilon naught az bar volt per meter. Unit of flux density is coulomb per meter square. Unit of the electric field intensity is volt per meter. That is what is the conclusion. Results are same as obtained for that of the infinite line charge by Coulomb's law. Whatever equation we had got for the infinite sheet of charge for the using the Coulomb's law, the same equation we are obtaining when we derive it using the Gauss law and the Gaussian surface. Okay, equations remain the same. In examination they can ask in two ways. In one way they can ask derive the equation, simple normal it will be a normal question, like derive the equation for the infinite line charge at a point P. Okay, that is a normal question. Then if they're asking derive the equation for the infinite line charge at a point P using the Gauss theorem, then you have to use this, whatever we have done now in our classes. Okay, whatever we are done in this class, we have to make use of that derivation and you all have to do. Okay, it may be for the line charge or for the infinite sheet of charge. Okay, the question it may appear for this infinite sheet of charges, derive the equation for the electric field intensity of the infinite sheet of charge for the infinite sheet of charge at a point P. Okay, using the Gauss law or using the Gaussian surface, then you have to do whatever we have done now, this derivation, whatever we did now. Okay, that has to be done. So it can be asked in two ways. If they ask the normal question, you have to do in the first method using the Coulomb's law. Okay, using the Coulomb's law, that also they may specify using the Coulomb's law. Then you have to do the first that we did the previous 2 or 3 classes back, whatever we have done, you have to do that derivation. If they ask using the Gauss law, then you have to use the Gauss law and do whatever we have done in today's classes. I hope it is clear to you all, students. Yes, students.
Yes, sir.
Yes, sir.
Okay, fine.
Yes.
Right. Any difficulty in this derivation, students?
No,
Any
sir.
problem in understanding? No. Okay, fine. Okay. Then the last topic in the module 1 is Maxwell's first equation. Maxwell's first equation. Let us derive this and then write the statement for the Maxwell's first equation. Divergence of electric flux density d bar is given by the equation. Equation for divergence. Try to recollect the test. I mean question. What I had asked to derive the equation for the divergence. Okay, or define the divergence theorem and then derive the equation, the test question. Okay, the divergence of electric flux density d bar is given by divergence of d bar is equal to limit of closed surface integral d bar dot ds bar divided by delta v as delta v tends to 0. We know that divergence is nothing but spreading factor, the spread factor or the spreading factor. If you are considering any point, I give the example of the balloon. Okay, if you are piercing the balloon will, air will blow out and finally it will become, the volume will become 0. The volume will shrink to 0. Similarly, if you loosen the valve of the cycle tire, okay, then the tire will become flat. Okay, the air will blow out and finally the volume at that point will become 0. Right. So that is the example of the divergence. So if I integrate d bar dot ds bar, okay, per unit volume, that is d bar dot ds bar per unit volume as the volume tends to 0, then that will give me the divergence of d bar. Okay, let us see the further equations. That is, this equation is also equal to dou dx by dou x plus dou dy by dy plus dou dz by dou z. Dou dx by dou x plus dou dy by dou y plus dou dz by dou z. Correct? This equation we have come across when we are discussing the divergence theorem. Recollect from there. Okay. According to Gauss law, we know that psi is equal to q, that is closed surface integral d bar dot ds bar. This is our Gauss law, whatever we are studying up till now in today's classes. Psi is equal to q, that is flux is nothing but it is the same as the charge, that is closed surface integral d bar dot ds bar. Take it as equation 1. Now we'll express this Gauss law in terms of per unit volume. We'll express it in terms of per unit volume. That is, we are dividing by delta V. Okay. The LHS will become Q by delta V, that is closed surface integral d bar dot ds bar divided by delta V. Okay. Q by delta V is equal to closed surface integral d bar dot ds bar divided by delta V. I am dividing by volume, delta V on LHS and RHS. Take it as equation 2. Now we know that according to the divergence theorem, the volume at that point will shrink to 0. What we mean by the volume shrinks to 0 mathematically, we have to take the limit as delta V tends to 0. The meaning of the volume shrinks to 0 or it becomes 0 when the divergence or the spreading takes place. After the spreading takes place or after the spread factor, then that in mathematical form, what we are writing it as delta V tends to 0. Therefore, here we are writing taking the limit as delta V tends to 0, that is volume shrinks to 0 on LHS, Q by delta V, limit as delta V tends to 0. The same limit I am also applying for the RHS, whatever RHS equation is here, that is closed surface integral d bar dot ds bar divided by delta V as limit as delta V tends to 0. That is equation 3. But we know that is volume charge density. Volume charge density, it is, how to define volume charge density, students? Charge per
Volume. Charge per
volume.
unit
Charge per volume. Yes, excellent. Charge per unit volume, Q divided by delta V. That is the volume charge density. that is, but limit of q divided by delta v as delta v tends to 0 will give us volume charge density at that particular point. Okay, that is our volume charge density. Above equation 4 gives the volume charge density at the point where we are finding the divergence. Okay, this equation 4, right, it gives the volume charge density at the point where we are finding the divergence. Hence divergence of d, this limit of q by delta v as delta v tends to 0 is equal to rho v. Okay, so if I substitute this rho v, right, in the equation here, in this equation, okay, so what I get, limit of delta v tends to 0, the closed surface integral d bar dot ds bar divided by delta v is rho v, correct, because this the limit of q by delta v tends to 0 is rho v, so rho v will be equal to this, rho v will be equal to RHS, correct, because this is rho v, therefore rho v will be equal to RHS in equation 3. Then what is the RHS of the equation 3? According to our definition of divergence, it is divergence of d bar. RHS of equation 3, it is nothing but, according to our statement, our definition, it is divergence d bar. Hence I can write divergence of d bar is equal to rho v. Divergence of d bar is equal to rho v. What is this divergence d bar? It is del dot d bar. Divergence is always written as del dot d bar, that is equal to rho v. Take it as equation. Next equation. Above equation is called Maxwell's first equation. This equation rho v is equal to del dot d bar is the Maxwell's first equation for the electrostatics. Remember, whatever we are studying up till now, that is all related to electrostatics, that is static charges. We have not yet dealt up anything about the dynamic charges. Okay, it is all about electrostatics, static charges, constant charges, fixed charges. This Maxwell's first equation is also called point form of Gauss law or Gauss law in differential form. Then how do we define this Maxwell's first equation? Looking into formula itself, we can define it. That is divergence at a particular point. Okay, divergence of the electric flux density at a particular point is equal to the volume charge density at the same point. Simple. If you remember this formula, right, del dot d bar is equal to rho v, then we can easily give the definition or the statement of the Maxwell's first equation. What it states, the divergence of the electric flux density at a particular point, that is equal to volume charge density at the same point. That is what is written here. The divergence of electric flux density in a medium at a point, that is differential volume shrinking to 0, is equal to the volume charge density, charge per unit volume at the same point. Okay. There are few examples I will try to cover in the next class. Okay. I will take one class at 1 o'clock, students. I will engage that class today. So be present at 1 o'clock. Then what all we discussed here, students, in today's class? We have covered the topic on starting from application of Gauss law for the point charge. Okay, we have derived the proof of Gauss law for the point charge. Right, this is our equation. Psi is equal to Q. Gauss law is proved. Then later we took up infinite line charge, and we have derived the equation using Gauss law and Gaussian surface. Is E bar is equal to rho L by 2 pi epsilon naught r AR bar. The same equation as we have obtained using the Coulomb's law. And we have later studied infinite sheet of charge. For the infinite sheet of charge, the electric field density, the electric field intensity is given by E bar is equal to rho s by 2 epsilon naught AZ bar volt per meter. Again, it is same as that we have derived using the Coulomb's law. And later we took up the derivation of the Maxwell's first equation. We have derived this starting from the divergence theorem, and then the equation that we obtained for the Maxwell's first equation is divergence d bar is equal to rho v, or del dot d bar is equal to rho v, which indicates that is the statement of the Maxwell's first equation is the divergence of the electric flux density at a particular point where the volume is shrinking to 0 is equal to the volume charge density, that is charge per unit volume at the same point. Okay, this Maxwell's first equation is also important from the examination point of view. Many times they have asked in the examination. Any difficulty here, students? Any difficulty here in today's classes? Yes, please. Anything not understood? Any point not clear? Okay. If you want to ask anything, you can ask. Harsh Gowda, any difficulty? Harsh Gowda?
No, sir. Understood, sir.
Understood? Good. Sankalp? Sankalp?
Yes. Yes, sir. Understood, sir. No problem.
Understood? Okay.
Yes, sir.
Right. Adarsh?
Yes, sir.
Adarsh?
Understood, sir. Understood, sir.
Everything is clear, Adarsh? Today's derivations?
Yes, sir. Yes, sir.
Okay. Lohit? Okay, fine. Lohit?
Yes,
Lohit?
sir.
Any problem in understanding, Lohit? Anything not understood? Any difficulty?
Understood, sir.
Understood? Okay.
Yes, sir.
Okay. Okay. If you are having any questions, students here, any questions? Pallavi, any questions? Daregowda,
No, sir.
everything you understood, whatever we discussed today?
Yes, sir.
Okay, fine. Right. So then we'll continue in the next class, students. We'll meet at 1 o'clock today. Then we'll solve few examples on whatever we have discussed today and in the previous class. Okay. Thank you.